So Ralph, that's
So we get started?
We should get started.
We got some pictures of us there, Nick, so everybody knows what we look like. That's
Absolutely.
nice. All right. So the theme of our webinar today is to discuss flushless sealing in primary, secondary, and tertiary systems in the wastewater industry, as well as sludge service. All right. So the question is, how do we apply mechanical seals in these services? We will also discuss the risks, because we've learned that, like all industries, the wastewater industry is evolving, changing, facing new challenges, right?
Absolutely.
So, what are the risks and how can we mitigate those risks, right? Our goal, obviously, particularly in the sludge area, but in other areas, is to minimize the use of flush, which would contaminate the product, and minimize the use of water, because water is the wastewater industry's product, right? So you don't want to use your product, right?
Absolutely.
So there are technologies available today that will allow us to do that, and there are ways or techniques that we can use to do that. So it's really about being aware of those. And so when we look at the wastewater processing general process, you sort of have above the line, below the line, right? So above the line is removing solids from the flow stream, obviously treating the biologicals in the water so that eventually you have a drinkable product.
Yep.
Below the line, the goal is to thicken the solids. So essentially, the heavy solids are directed below the line, sludge processing, and then we use microbials to digest the sludge, because we really don't want to take solids out, right? And everything else we want to either go back in the water processing or get rid of. And then ultimately you develop a sludge cake or solid material, right? And in this area in particular, flush is very undesirable, put it that way, because the role in sludge processing is to take the water out, right? So in particular in this area, we definitely don't want to add water, right? So in some of the services above the line, people will use water and grit and those kind of things. They can use what are called flush, right? We'll talk about what is a flush and define that.
Okay.
But there are ways to seal those services without using water as well. So we're going to talk about that. Okay.
Excellent.
So when we look at the overall process, these are some of the services that we're going to discuss. So when we begin the process, that is the influence side, as the fluid starts to enter the plant, it's generally provided through lift stations. So these lift stations are positioned in different areas of the municipality, and there are pumps there that pump the influence. So essentially essentially, right, comes from this area into the plant. And they may be pumping from a wet well, shown on the left, right,
Okay.
or a dry well, a dry pit, right? So the idea is you could have a submersible pump in the wet well that would pump to the plant, or you might have a wet well and a dry pit centrifugal pump that's located adjacent to the wet well that would lift that fluid.
Okay.
So what happens is the water from the municipality flows into the lift station and it lifts it up. That's its purpose, right? Now, one of the challenges in this area is it's remote in many cases, right? And so you may not have flush water in this area, right? So, the challenge in this area is, what happens if you face challenges like fiber in the fluid, right? And that fiber will collect in the pump and can cause issues for the seal, right? So how do you address that challenge, right? So we're going to talk about this. This is some of the newer challenges that some municipalities face, not all.
Okay.
The information that we've been able to collect tells us that dry wells in near large municipalities are more susceptible to fibers clogging, but not exclusively. Affluent areas too, right? So we're going to talk about this problem. Anyway, so this is where it all starts. And these are examples of dry well pumps in a lift station, right? So in this particular case, these are centrifugal pumps, and they will have a mechanical seal, and the seal will be on a vertical shaft here, right? And so the fluid will enter the pump, in this case, probably from the bottom, and then there you have discharge on the side here, right?
Okay.
So that's what that looks like, and they may be enormous. These are good-sized pumps. There are very, very large pumps too. So all different sizes. So let's talk about flush for a second. Now, the traditional solution in mechanical seals is a flush. And the reason is the other description for a mechanical seal is a liquid lubricated face seal, right? So what that means is, in our diagram here, at this point right here, where the so-called seal faces, these are highly polished rings. One is pressed against to the other by a spring to force them together. The interface of those two rings is lubricated by the product or fluid in the product, right? Whatever we're pumping. And therefore, that fluid is critical. And if that fluid will not lubricate, penetrate and lubricate that interface between those two rings, we have what's called dry running. And dry running will generate heat, cause damage to the rings, and damage the elastomeric parts. Absolutely. So the assumption with mechanical seals or liquid lubricated face seals is that you have good lubrication at what we call the primary seal, the interface between the two seal faces. And that's not always the case, right? Especially in the wastewater industry. So in the past, since these folks produce water, the assumption was, well, let's just flush it, right? And let's define flush. So a flush, or a clean flush, is defined as Piping Plan 32. And Piping Plan 32, that plan number is in ANSI B73.1, API 682. It defines each of these piping arrangements that we're going to discuss. I should say most of them, not all of them. I'll explain. If the plan is generic, that is, it's not specific to a particular manufacturer, it will be in the standard. However, if the plan is specific to a manufacturer, it will not be in the standard. So what has happened is manufacturers have come out with new technologies and invented plans to describe what they're offering to make it easier for customers to discuss and order them. Okay? So in the case of Plan 32, what we have is a clean fluid, generally water in this industry, and that fluid is provided, it could be provided through a flow meter, which is a real good idea.
Absolutely.
There may be a pressure gauge. There should always be a check valve, particularly in this industry. And that fluid will then enter the mechanical seal and enter the pump. It will pass between the shaft and what is called a throat bushing or a restriction bushing. And that's an important component. And what's interesting is with Plan 32, a lot of people forget about using that component, but it's important, and I'll show you why in a moment. And that fluid passes into the pump. So this clean fluid provides the lubrication at the primary seal that we need, right? Now, what's interesting is the check valve. The check valve prevents backflow of the product back into the supply of the flush. Okay. Critical component, right?
Absolutely.
And the other interesting thing is the flow meter. That is, if you have no flow, means you do not have enough pressure for that fluid to enter the seal.
Absolutely.
Right?
That's obviously a problem.
And that shows you that you don't have any flow. May not be a problem, may be a problem, but depends on how you want to set it up.
Absolutely.
So, and we're going to talk about Plan 32 and how you can set it up to act as an insurance policy. So here's the thing. Plan 32 means the flow is continuous, right? But you don't necessarily have to set it up so the flow is continuous. You could set it up so that if the pressure were to drop to vacuum, you would get flow. But if the pressure increased positive, the check valve would close and you wouldn't use flush water. Okay. See what I mean?
Absolutely.
So the advantage there is you're not using water. Now, round numbers, if you run a gallon a minute, 24 hours a day, 7 days a week, that's 500,000 gallons of water a year.
That's a lot of water.
That's a lot of water.
A lot of water. Right?
So the idea here is to set up the flush to try to minimize the water usage, right? If you're going to use it as an insurance policy. The nice thing about flush is it covers all sins. You know, if the pump runs dry, if there are fibers in the stuffing box, if there's sludge in the stuffing box, it will keep that seal clean and well lubricated. That's the nice thing. The bad news is 500,000 gallons a year, right? Yeah. So what people have been working on and offering is new technologies to avoid having to spend that money on that water. Okay? So that's what we're going to talk about. So Now we talked about the restriction bushing. Now the interesting thing, some people call it a throat bushing, restriction bushing. That's this bushing at the bottom of the box. The amount of water that you use is directly related to the gap between the shaft and the restriction bushing, right? So, and what's interesting is the length of the bushing will also have a huge effect on that water usage. So let's take a look. This is Chesterton's restriction bushing flow program. So this is an online calculator that our sales folks can use and use all the time. Our engineers use all the time. And what Chesterton did was we did a series of tests in the lab. Ray Clark, Dr. Ray Clark, he's a computational fluid dynamicist. These are people that study fluid flow.
Okay.
So Ray said, I'm interested in, problems that the railroad faces. So we said, well, here's a problem, Ray, the shaft's rotating underneath this bushing. So the question we had was, how can we estimate the amount of fluid, flush fluid, that will flow underneath that bushing into the pump? So Ray did a series of testing in our labs, and he came up with an algorithm. And the algorithm is based on Reynolds number, but in essence, you either have turbulent or laminar flow. And the Reynolds number tells us what kind of flow you have, and then at that point, you can estimate how much flow you have. And what Ray discovered is the most important factor was this gap between the ID of the bushing and the OD of the shaft and this length, right? So he set up this algorithm, and our IT folks very nicely put this online for our sales folks and our engineering folks.
Excellent, excellent.
And what you can do is you can input variables. So in this case, I input 4-inch shaft, and what it does is it comes back and says the ideal bushing inside diameter is 4.012 inches. And I selected a 1/2-inch long bushing, and I selected a flush pressure 15 psi higher than the sealed pressure. That's typically what we recommend for flush pressure plant 32.
Okay.
And in this case, I selected ambient temperature. Now here's the most important thing. I input stainless steel shaft and carbon bushing. And the reason we put these materials in, it turns out that they have different coefficients of thermal expansion, meaning metal expands faster than carbon. So it affects that resulting gap at 70 Fahrenheit. And I put in the viscosity and the specific gravity of water. In this case, water is very popular. So what it says in this case, because of these conditions, the gap is 6 thousandths on each side, which makes sense, right? It all adds up. They're benign. At higher temperatures, the gap gets smaller. At lower temperatures, the gap gets bigger. So what we were able to do is to do the calculation, and what this tells us is with a 1/2-inch long bushing, the flow rate is 7.3 gallons a minute. Okay, so that's kind of our starting point. Okay. The question is, do we have enough room in the pump to add more bushings? What if we put more bushings in behind the seal, right? Would that affect the flow rate? So let's see on this next slide. Now, in this case, we put in 5 bushings. So now, instead of 1/2 inch long, that bushing's 2.5 inches long. Okay. And look at the effect on flow rate. We've dropped the flow rate to 2.4 gallons a minute, or 7 gallons a minute, 7 whatever. So you'll notice that the axial velocity underneath that bushing is 15.4 feet per second. The seal industry basically says, has all sort of agreed that desirable minimum velocity is 15 feet per second of fluid flow between the bushing and the shaft. That will eliminate solids contaminating the seal. If you talk to Ray, Ray is a little bit more aggressive. He lives in a theoretical world. This is a sort of a conservative number. So if you have 2.5 inches inside the seal, inside the box, below the seal, what you can do is use restriction bushings if you have to use a flush to reduce the amount of flush that you use, right? So the beauty of this technique is nothing really different than you're already doing. You're just using 1/3 of the flush that you were using before. Absolutely. To do the same thing, right? So that's one way to improve the water usage for plant 32. Okay. If you have to use a flush. Don't always have to use a flush, but that's one thing to consider. Oh, so we have poll question number 1. So let's open up this poll question. It looks like we got quite a few folks joining us today.
Yeah, I got 21 participants right now.
That's a good group here. Let's take a look here. So I'm going to open this question, and the question is, increasing a restriction bushing's blank will reduce the flush flow required. Outside diameter, length, inside diameter, or groove width. Let's see what folks vote here.
All right.
And once everyone's voted, we'll broadcast the results. We get 21 folks, so we'll broadcast it. Let's say 15. Some folks get a little nervous, whatever. We don't want to make people uncomfortable. It's pretty good. Okay, so let's broadcast the results. So you see, 11 folks have said length, 3 folks have said inside diameter. So we have some scientists out there. Because, remember, Ray said that gap was critical. Now here's the rub. The problem is, when you have a gap that's too small, we found that the shaft, in some cases, will orbit the true axis and just open that gap up. Or it rubs and causes other issues with heat and this kind of stuff. So yeah, you can reduce the inside diameter and reduce the flow rate, but there's risks there. So using the standard gaps that we established in the tool is very safe, and that's why we set that up. So the answer I was really looking for is length. However, you get credit for inside diameter too.
There you go.
All right?
That's good.
Okay. So I'm going to end this and hide this. All right. So let's keep going here. All right. Now, what's interesting is a lot of plants use packing. The mechanical packing is a great solution in a lot of wastewater pumps. And what's interesting about packing is it seals the rotating shaft via intimate contact with the shaft. So here's 3 rings of packing, and that intimate contact with the shaft is where the sealing really occurs, right? That occurs when we tighten up the gland.
Yep.
However, in their industry, they would use a flush to prevent solids in the fluid from becoming embedded in the packing. Because if those solids become embedded in the packing, then the packing will start to act like a tool wearing the sleeve and damaging the seal and causing leakage. So it turns out that there are folks that have developed technologies, and I think Paul has a term for it, active technology, active bushing technology. I have it in the slide later on. And these folks have designed a device that incorporates a lantern ring and a groove. And that groove acts to prevent solids from working its way between the shaft into the packing. So using this technology to replace the bottom 2 rings of packing to provide good access for the flush, that is, that lantern ring is never going to shift due to compression of the inboard packing rings, will protect the packing, allow it to run longer, but also allow you to use less flush, right? So you can reduce the amount of flush that you use on a 5-ring set using this device along with 3 rings of packing, right? So this is a better way to use packing in a pump and reduce your flush.
Perfect.
Okay? So restriction bushing with mechanical seal, this device is called the spiral track with mechanical packing. These things allow you to reduce flush, okay? We haven't eliminated it yet, but we're moving in the right direction. So this is an example of a lift station, and in this particular case, I mentioned earlier that these are lift stations. Pumps can be very, very large. This particular one, there's 3 or 4 of these. There's actually 3 pumps. There was a backup pump, whatever, in a lift station down in Pennsylvania. And these are horizontal pumps. Now, what's interesting about these pumps is they're driven by a motor that's a couple of stories up. So there's a big shaft, line shaft that goes down that then is coupled to the pump itself. And the reason is because if this area gets flooded, you don't want to destroy the motor. These motors are very expensive.
Absolutely.
Right? So what that does is it drives the shaft, and then the shaft has to be sealed. And in this particular case, this customer used a split mechanical seal, and they flushed it, right? So here's the flush line right here. So, this is a typical situation. These seals have been in service for a long time. This replaced packing, and the issue with the packing was, again, the solids were becoming embedded, right? So this particular customer decided to use mechanical seal. Now, this lift station doesn't pump sewage, it pumps stormwater runoff. So the idea is when it rains a lot, the sewage become overflowed, and it goes into this wet well, and then that's pumped to the wastewater plant to process. So this is more of an overflow. So they're not run all the time. They're kind of run intermittently, right?
Absolutely.
So, so that's giving an idea. So what you're going to get in there is like sand and dirt and that kind of stuff as the water flows in to the sewers, right? So all that grit and stuff. So the flush helps to isolate the seal from the fluid and lubricate the seal. Also, with the seal mounted vertically, the flush helps to make sure the seal faces are lubricated, right? Because in vertical service, you may start that pump and there might not be water in it yet, right? So you open the valve, there's going to be an air bubble there, and that air bubble has to work its way out, right? So the flush, you turn the flush on, covers all sins. Doesn't matter if there's air in there or not, right?
Perfect.
So, so that works, right? But it's expensive. So,
Absolutely.
but that's an example of how that's used. Here's another lift station, another example. Again, very large pump, very, very large pump. These are a couple, so they're relatively low speed. What's interesting about this particular pump is that there was bearing damage at the bottom of the pump down in here due to leakage, right? So you have, it essentially looks like horizontal split case pumps, see the casing here. And so you have seals on both sides, right? So the purpose of this seal was to protect the bearing below it, right? So they were having issues with leakage from the packing that was causing bearing failure, right? So that would be a reason to go to a mechanical seal over packing, right? With this type of an arrangement, right? You're protecting the equipment. So again, this particular one was flushed. So you see the flush line right here. Okay. Here's another influent pump, very large pump. Now, what's interesting is this particular customer decided to use a split mechanical seal with the active bushing technology, the active spiral track technology in this particular service. And the reason is they did not want to use a flush if they could avoid it. Now, in this case, they didn't completely not use the flush, but just like the device is used with packing, if you use a device with mechanical seal, you can reduce the amount of flush that you're using. And you notice they have the valve right here, right? So what you can do is you can reduce the flow. You can valve the flow till you get to the flow rate that you desire. So you're not eliminating the flush, but you're reducing it substantially, right? So that's a positive thing, put it that way.
Okay.
So a step in the right direction. Now, this is a problem. And this is called ragging out. And we have a video, so why don't we show the video?
All right.
Let's do this. Share my screen. Share. And there we go. So now, I'm not advocating any particular pump manufacturer with this video. This particular video just happens to show the problem. So we have a plant here in upstate Washington, and there's their raw sewage pumps. And the problem that they're having with these raw sewage pumps is as they were taking influent in, the influent contained fiber. Here's Tim Scott explaining the problem. So this is the problem. So what this is all those wipes, all those baby wipes and all that kind of stuff. And they use them, people throw them down the toilet, and they ended up right at the suction side of the pump. And what happens is they call this ragging out, okay? Now, remember, we explained that mechanical seal, it's got to be lubricated by liquid. Well, this fibrous material will collect in the seal chamber and starve the seal of fluid at the primary seal. That's the problem, right? So, the question is, how do you solve this problem? How do you solve it with the pump? How do you solve it with the seal? So, I'm going to stop sharing that. I'm going to go to this. So the problem, let's go to this, of ragging out is a common problem, but what's interesting is it's harder in some areas than in others. So to avoid the issue in the pump, there are pumps that have cutters on the suction side. So this is an example of a cutter pump. There's a bunch of different manufacturers that make these types of pumps. I'm not advocating for any particular manufacturer. I'm just making people aware that they exist. Okay. And if the customer can use this style of pump and cut this fiber up so that it passes out the discharge of the pump here, as opposed to collecting in the seal chamber, fantastic, right?
Absolutely.
That really helps the seal vendors. They're designed to break up clogs and prevent ragging. This is the YouTube video example of YouTube. They're shaped to minimize flow restrictions, and it's a hardened cutter. So usually they're hardened, and very often they're adjustable. So these cutters resist clogging. Here's another example of a cutter. This happens to be Cornell's version of it, whatever. So these blades rotate adjacent to these stationary elements, and as the fiber enters here, it's cut up by this, right? Now, if the pumps are horizontal, this fiber is usually lighter than water, so it tends to go to the highest point in the system.
Yeah.
But if the pumps are vertical, the fiber will collect in the seal chamber, and it will starve the seal of fluid, right? And if it starves the seal of fluid without a flush, it's going to fail.
Absolutely.
So in the past, customers have just flushed the seal, but the problem is using all that water is very expensive.
Expensive, absolutely.
So people don't want to do that, right? Yeah. So then the question is, well, what do you do? So this is one option. So this is called a dual seal, and in this case, what you have is an inboard primary seal and an outboard primary seal. And you have a reservoir, a tank, and this tank is filled with water, and this water is circulated by the dual seal, and this tank is pressurized by a line pressure. So you could also pressurize it with compressed air or nitrogen, something like that. You like that seal to be pressurized at least 15 psi than the sealed pressure in the pump. That way, this water will lubricate the inner seal and the outer seal, right? So what you have here is a seal that's impervious to ragging out. If you have fiber collecting all up inside this seal chamber, doesn't matter, right? Seal will work.
Perfect.
Okay. So this is called the dual seal, and dual seal is sort of the most impervious approach to avoiding this issue. Put it that way.
Okay.
What's the bad news? Cost. It's expensive. Dual seals are expensive, right?
Absolutely.
Plus you got all this support tank and all this kind of stuff, right? And you got to make sure there's water in this thing, right? And a lot of times the lift stations are remote, right? So you don't necessarily have a lot of water out of that lift station, right? So how are you going to do that, right?
Absolutely.
So this is some of the challenge that we have to think about, right? When we have a lift station, do we have fiber in our flow? Do we have, before it gets to the lift station, some way to remove this fiber? There are machines that do this instead of doing it at the pump. Are we using pumps that are chopper pumps? Are we using conventional pumps, right? So these are all things to consider. But anyway, so as a seal vendor, this is one way that we can solve this problem if the customer is willing to do that. Now, in preliminary and primary treatment, and that's coming into like lift stations, Chesterton has our wastewater guide. And in our wastewater guide, we have recommendations. So what we're showing is a split seal, hard face, and plan 32. That's our standard recommendation. Okay. The other option would be a cartridge seal, hard face, soft face, plan 32, and or mechanical packing and a flush, right? So our conventional solution is with a flush, because that's what we see a lot of industry does. But a lot of industries trying to get away from flush, right? So today, a lot of plants look at flush like that's their product. That's what we're making. So we want to use as little of that as we possibly can.
Absolutely.
So what we've already described are use restriction bushing. That's one way to do it. Use a spiral track device. That's another way to do it to reduce flush with packing. You can completely eliminate flush with a dual seal, right? So having fluid from a tank, pressurizing it, that will completely eliminate flush, but it's more expensive. So now the plot thickens, because then the question is, well, can we have a solution that works without a flush that does not require dual seal?
Exactly. What's
right?
the ROI?
What's the ROI? Yeah, like give us the cheapest thing that's gonna work, right?
Exactly.
So that's where we live. So that's where this is where things get interesting. But before we get to that, let's do our second poll question.
All right.
So I've opened the poll. Ragging up or ragging out causes a mechanical seal to run dry with reduced face load, clogging, run with separated seal faces, clogging, all of the above. What do you think, folks?
Seeing a little bit of both right now, huh? All the above, all the above.
So what we're going to do, we got about 25 folks. We'll broadcast the results when we get to about, oh, there we are. Okay, here we go. Broadcast results, and 76% of you said all of the above. I would have to agree, but I wouldn't disagree with running dry either. Running dry is going to be the first issue. The second issue is that fiber will collect around the seal faces and prevent the springs from pushing the faces together. So it will cause reduced face loading. It may actually penetrate the seal faces and cause them to separate. So it's very bad any way you look at it. So you just don't want it to happen.
Absolutely.
So very good, very good. So let's do this. So what we're trying to do is mitigate that, and we're going to talk about ways to do that in a moment. But as we enter the system, one of the pumps that we see in the wastewater industry are grit pumps. And so this is a diagram of a grit pump, which is feeding a cyclone, or being fed from a cyclone separator. And let's see, so the solids come in through, let me get that thing, come in through here. They are separated by this cyclone feed, right? So the higher velocity material comes out here, and let's see, from grit chamber. So once we take fluid from the grit chamber, it goes up into the cyclone. We get high speed here, high speed separation. The solids go down in here. So it's all about separating the grit from the fluid. Okay. So the purpose of the pump is to increase the velocity of the fluid as it feeds the cyclone to separate the solids from the fluid. And then there's an overflow up here, and there's a fluid is removed at some other point in the cyclone. So this whole clarifier here is to remove these solids. Mm-hmm. So this pump generally sees what are called settling slurries, meaning the solids will settle out of the fluid. And so it's a fairly aggressive service in terms of a slurry, right? Mm-hmm. And again, you have a process here where you don't want to add more fluid, because if you're adding more fluid, the whole purpose of this is to separate the solids from the fluid. Absolutely. Right? So, so these are examples of grit pumps. So they can be what are called recessed impeller or vortex style pumps, and we see a lot of that as a grit pump. Not always, by the way. Now, why is that? The reason is because these slurries are abrasive, and in a conventional centrifugal pump, the grit can wear out the impeller, right? And so, over time, you have to keep repairing it, put an impeller, whatever. Absolutely. You can use harder materials. Some people do that. They're not always recessed impellers. So we've seen grit pumps that are not like that as well. But anyway, so that's one of the things that we tend to see. It's an example of one. And here is a solution. So in this particular case, and it was interesting, this happens to be a Chesterton 221 first generation split seal. And that is an Owenco grit pump, and so they are flushing that seal, right? So the interesting thing about the split seal is it mounts completely outside of the seal chamber. So what it allows you to do is to mount a close tolerance restriction bushing for the length of the chamber, right? So remember we saw how earlier a restriction bushing length would affect the amount of flow going into the pump, yep, right? Absolutely. So the beauty of that, of the split seal, is it gives you that space to do that, right? Because it mounts externally. So anyway, so that's what they do here. So yes, they are using a flush. They're surrounding the seal with clean fluid, but the amount of fluid that's going into the grit is substantially less than into the pump is substantially less than if you had no bushing there at all, right? Or even a half-inch long bushing. Absolutely. So that's one of the advantages of split sealing in wastewater services. It gives you that whole box to try to eliminate or minimize that flush. I would say minimize that flush. Mm-hmm. Another option would be to use a spiral track or a device that removes those solids, and then you could eliminate the flush. We'll talk about that in a little bit. Anyway, so there's an example of a solution. Here's primary sludge, and now when we get into the sludge side, again, it's very similar in terms of the grit process. You're trying to remove the water, right? It's all about separation, because you're reacting to biologicals and to break down the sludge, and then really what you want to do is separate the solids that cannot be broken down from the biologicals. The biologicals can be handled with the water, and those solids eventually go to landfill, become fertilizer, whatever you want to do with that, right? So So primary sludge, in this particular case, they use a split seal with a flush, right? Now people say, well, wait a minute, you don't want to contaminate it. Again, fill the box up with restriction bushing, and I've actually seen situations where they'll fill the box up with restriction bushing or a series of polymeric isolation type bushings, and they'll run water in and out of the split seal to try to minimize the contamination in the sludge. You're surrounding the seal with clean fluid, right? It's not a dual seal, it's still a single seal, but the bushings inside the box are acting as kind of a flow restrictor. The fluid will take the path of least resistance. So if you provide a drain, you're going to reduce the amount of fluid that goes in the pump. In sludge, you definitely want to do that. They do not want to contaminate that sludge. They can possibly avoid it. So the other option is a dual seal. I'm going to talk about that. So here are Chesterton's recommendations for in the wastewater guide. Now you'll notice what they've done is they've said, oh, we don't want to use carbon in these processes because they're a lot more solids. Okay. So what they're doing is they're recommending what are called hard face, or seal face materials that are not prone to abrasion. They are still asking for a flush, but just because they ask for a flush doesn't necessarily mean that the flow rates are so high that they're unacceptable. You can really drop those substantially. The other option is a cartridge seal, and then there are mechanical packing options here as well. Now, active throat bushing technology. Great, we finally got to that. So there are folks in the industry who have developed a technology that uses the energy of shaft rotation to remove solids from the seal chamber. And I think it's probably a good time to show folks what that looks like.
Sounds good.
So let's do that.
So I'm interested myself.
Share my screen. I'm going to share this. So this is an example of an active throat bushing mounted inside a pump. So we have the mechanical seal sort of to the right of the screen, and we have solids, and these are settling solids. So think of like grit, even some sludges will settle out of solution. That's why they have separators and clarifiers and that kind of stuff. The density of the solids allow them to separate from the fluid by gravity. Well, in this case, what these folks have figured out, I'm going to keep doing this, what these folks have figured out is that the shaft, as it rotates in the fluid, will cause the fluid to rotate. Not at the same speed, but it's still going to rotate in the seal chamber. So what they cleverly figured out is if you shape a device such that you take advantage of that rotation, it will act to remove the solids. So you will have clean fluid around the mechanical seal. And that's what that is demonstrating right there. So, it happens very quickly. Our simulations show, 20, 30 seconds, max for removal. This video, it's a lot quicker. It depends on the speed of the shaft, size of the shaft, density of the solids, all that. So in settling slurries like you find in wastewater, this is a solution, and this works. So this particular device also has a groove that is mounted at the 12 o'clock position for horizontal shafted pumps that allows air to escape. So the seal is completely immersed in fluid. Problem is, in a conventional pump, air gets trapped. So the seal is actually running in a mixture of air and fluid, and that causes issues. If you immerse the seal completely in fluid, like the lubricated face seal, it works much better. So this, that's an example of what that guy is. So let me stop sharing here. Back to here. So this active throat bushing technology can be used with split or non-split seals, all right? And we developed piping plans we call Plan 33H, and that's a device that can be used without a flush, and Plan 33S, and this is a device that is used with a significantly reduced flush. Now, the people say, well, why do you need a flush with 33S? The reason is because there is no groove that allows air to be vented from the seal chamber. So you provide a small amount of flush to displace any air around the seal. What you find with split seals is because of the splits, the gas eventually will find its way out. It happens not real quick, but quick enough in many cases. So Some people use Plan 33S without a flush. I think it's always a good idea to have a flush available, and this is why. What you find in some seal chambers, you think the seal chamber is flooded with product. It's not. And we've learned this in some services, right? So what you can do is you can build an insurance policy. And your insurance policy is you set a check valve on your flush line. You set a pressure regulator on your flush to 30 psi max, right? So if your box pressure is below 30 psi, meaning let's say there's air in that box and there's no pressure in there, the check valve will open and you will be injecting flush into the seal up until there's water in the seal chamber. Once there's water in the seal chamber, the check valve closes because now you have pressure in there and you don't use the flush anymore. Perfect. And the beauty of it is it's automatic. You don't have to turn it on and off, right?
Absolutely.
So this is an easy way to set up an insurance policy with your spiral track and with your split seal, hard face or not, in wastewater service, right? And particularly in vertical service, right? And so there are situations, and I'm going to share one, where in vertical service, it takes time for fluid to find its way up to the seal. And what we do not want is the primary seal to run without face lubrication, lubricated face seal, right? Mm-hmm. So setting up this plan this way really eliminates a flush, but provides, we'll call it start and stop lubrication, right? We have, actually I was out in California and I was talking to some of the folks out there, and what they were doing in some of their pumps, some of their seals, is they had a timer. So when they started the pump, this flush fluid was on for about 20 minutes, and then it shut off. Mm-hmm. And then when it stopped, it ran for about 20 minutes, cleaning all that area out, and then it stopped, right? So that was sort of the alternative to this, right? Now, the bad news with this is when the pump shuts down, the flush will flow, right? So the thing is, you would want to use this in a situation where the pump is always running, right? Okay. So then hydraulically, if the pump is running at low pressure, you're covered, right?
Perfect.
However, if the pump starts and stops and starts and stops, you probably want to use a solenoid valve instead, a valve that will run flush just at start and just at shutdown. Okay. So that's where you use the two different approaches, okay?
Perfect.
So this is an example of a split seal with a active throat bushing, right? So there it is mounted in the bottom of the seal chamber there,
okay,
right? Now, in this particular case, unfortunately, this is not horizontal. This is vertical. And this is what this looks like here. This was in return-activated sludge, and that was the solids concentration. Temperature's ambient. These are the pressures. You notice how low the pressure is? Suction pressures, 5, discharges 20. We estimated 8 psi sealed pressure. Here's the shaft speed, right? We have the equipment numbers. And the seals failed, right? Now, these seals had the active throat bushing technology. They did not have a flush. They had no augmented technology on them. And, we confirmed the rotation was correct for the active throat bushing technology. The seals had what is called a Plan 13, a vent line to vent the air out, right? So you figure, all right, with the Plan 13, the gas should vent out, should be fine. Mm-hmm. And the fluid was a acetylate slurry to return activated sludge. It was fairly straightforward and really should have been a layup for this approach, right?
Absolutely.
But that's where you learn. So this is what this looked like. Now, these casings are probably 5 feet in diameter. Right?
It looks like a big pump.
Yeah, they had, I think, 6 of them in a row. And they're all vertical mounted, right? Okay. So what's interesting about this particular case is that the suction came from the bottom here, right? And this is the discharge, right? So the casing is at the highest point in the system, right? And what they were pumping is return-activated sludge. And it turns out that this sludge is these microbes in it is breaking down sludge, right? That's its purpose, right? Mm-hmm. So when they break down the sludge, what they create is methane. And the methane eventually fills up literally this entire casing. So this is the Plan 13 right here. See this line? That's your suction reserve.
Okay.
And what you would expect to see is if there is fluid up to, say, this point in a seal chamber, when you start the pump, you'll start to see gas bubbles coming out here and everything will be fine. The seal will be immersed in fluid.
Yep.
When they started these pumps up, we never saw fluid.
That's a problem.
That's a problem. Yeah, the whole casing was full with gas, right? So the contractor who was working on the job actually demonstrated this, and they opened this valve right here on this pump casing, and literally methane was venting from that line for at least 2 minutes. I timed it. I couldn't believe how much methane was in the casing. So now the operators were supposed to vent the casing so that the seal was immersed in fluid, but they weren't doing it, right? So when they started the pump, what would happen is the seal faces would run dry and the elastomers would melt. So let me see if I have a picture of this. Yeah, so the seal faces were sort of warm. The elastomers were actually melted here. These were become square from heat. And so you got this kind of leakage. Now, not unacceptable. You could run it that way, but still, unacceptable to the customer. Mess and
oh, absolutely.
So, the question is, what do you do? Because in this case, the seal was running dry, right? So the answer in this case, see, this is what we're trying to do is vent the air off, vent the gas off. Problem is too much gas is filled in the casing. So this is great if you have an air bubble in the seal, but this is not going to work if the whole pump is full of gas, right?
Absolutely.
So in this case, one solution would be to run a flush to the seals for, say, the first 20 minutes and then shut it off, right? At that point, once that pump is started, it's actually pumping fluid within a couple of minutes. The seal faces are lubricated, you should be fine, right? And also run it when it's shut down, make sure there's fluid between the seal faces. These pumps are intermittently run. So, pumps, 2 and 6 are run, and then 3 and 5 are run, and then, 2 and 4 are run, or whatever. So they're not run continuously all the time. So that was another part of the problem, start-stop, right? If we had set this up with a flush with a check valve and a pressure regulator, the flush would be going all the time in the pumps, and that would be unacceptable as well. It would be good for the seal. It would allow the pumps to start easier, but they use a lot of water.
Very expensive.
Very expensive. So the solenoid approach in this particular case would solve this problem. The other approach would be a dual seal. That would definitely work, but again, very expensive. So the spiral track can do its thing once it's immersed in fluid. If it's not immersed in fluid, it's not going to work, right? Because there's nothing to remove, right?
Absolutely.
The seal needs lubrication. So again, venting is critical. Now, the customer knew this. And you see this device right here? That is a float valve. So what they were doing is mounting float valves on these casings so that they would automatically vent off the gas. And it looks like this. So here's an example of a float valve. This is a crude version of it. But what you have is a float inside this housing and a valve that allows air to vent or gas to vent, right? And so when you vent the gas, eventually the fluid comes up to a level where this float rises and it closes that valve. So it's automatic, right? Problem they had with that is these pumps are so big that when you were venting the gas, the methane alarms were going off up on the top.
That's not good.
Right, because there was so much methane being produced, right? So the problem they had was, how do you get rid of all this methane,
Absolutely.
right? So that was the issue, and that's what. So sometimes system issues are really the challenge, But in this case, the answer would be a start-stop flush, I call it.
Okay.
Now that is not a continuous flush. That is a start-stop situation to protect the seal. So this is what we found in the failure analysis. Plan 13 wasn't designed to vent that kind of gas. So it just wasn't big enough to allow the gas to escape. And then it was causing dry running and melting of the O-rings. So, we made our recommendations. And the reason I'm explaining this to this particular group is you may see this. You may see where, I'm using spiral track, or I'm using this active throat pushing technology with split seals, or even non-split seals with hard face, these 100 different pumps, I got no issue. This one over here, it keeps failing, right? Why is that? Well, the question is it possible that fluid is not in the pump or not in the stuffing box, right? And if that is the case, you're probably going to need to either use a start-stop flush or a pressure-regulated flush, one or the other, because there is a point during the operation of that pump where those seals are running dry, and that's the problem. Right? This is what we're seeing. The other thing is sludge. Like in some services, the amount of solids can be so high that spiral track can't handle. It's just more sludge than it is fluid. And in that case, flush is the only way to solve that problem.
Absolutely.
So, all right, so that's that. And let's see here. Oh, we got poll question number 3. When processing sludge, the best way to prevent dilution from flush is to use a split seal with a flush and a spiral track bushing, use a non-split seal with a flush and a restriction bushing, use a non-split seal with hard faces and a flush and a spiral track, use a dual seal with a barrier fluid. We will broadcast the results once the majority of you answer the question. We're getting some grudging answers here, Nick.
Absolutely.
One or two folks are answering.
We're up at 7 now.
Hey!
9.
9.
We're moving.
Okay. All right. Well, let's broadcast. We've got. Should we broadcast? What do you think?
Give it a couple more.
All right.
Give it a couple more.
It's fun to watch. It's interesting to see the contention. Put it that.
Absolutely.
All right. Let's broadcast.
All righty.
All right. So what we see is 71% of you have said dual seal, and that really is the answer I was looking for, because dual seal you're not going to contaminate the process.
Absolutely.
Split seal with a spiral track is the other way to do it, in that with the spiral track, what you can do with hard face is you can reduce the amount of flush that you're using.
Yeah.
But you're still using some
You're
flush.
still using some flush.
Right.
Absolutely.
So whenever you use a flush, some of it's always going in the process. So in sludge services, generally dual seal is the only way to do it without a flush completely. And I'm talking high concentration sludge too. So, but in lower concentrations, you can do it with hard face, and a spiral track without a flush. Perfect. So, okay. So let's end this poll, and let's keep going here. All right. So here's our sludge processing. Here's our standard recommendation from our wastewater guide. And so there's a whole series of different services, including raw water and let's see, super natant and finished water and thickened sludge and sludge cake. And generally we give concentrations, and we talk about thickened sludge, we're 10 to 15%, sludge cake 10 to 25%. And what they're basically saying is use hard face, and flush the seal if at all possible, right? Because again, very high concentration sludge, how can you get fluid to the primary seal? That's the trick. This is a conservative way to do it.
Mm-hmm.
Dual seal is another way to do it. What's interesting is just because this is our standard recommendation doesn't mean you can't do it another way.
Of course.
It's just what we've published. We know works, right? So there are other ways, and let's see some of that. So here's an interesting one. So here is a return activated sludge pump. This is, it looks like our old 221 split seal, and this was 8 years runtime when this photo was taken. And this particular one is set up with a flush. Again, the seal is outside of the box. Fill the box up with bushings, reduce the flush rate, right? Surround the seal with clean fluid, you got it, right? So that really protects the seal. Here's another one set up this way, waste activated sludge, and that looks like I'm not sure, it almost looks like a cartridge seal there. But again, this particular one's flush. What's interesting about this one is, and this pump is made for slurries, is the flush line goes into the bottom of the box, right? So what's interesting about that one is they also have another line here going into the seal. So they're cleaning the area in front of the bushing, and they're putting fluid around the seal in the back of the bushing. So it's kind of an interesting way to do it. Thought that was different. I figured I wanted to share with folks.
Absolutely.
But again, they're flushing too, right? So we're trying to minimize that.
Absolutely.
So one thing you see in a lot of sludge services are what are called rotary lobe pumps. So this is an example of a rotary lobe pump. So this pump has 2 lobes, right? And these lobes rotate relative to each other via this gearing, okay? And the motion of these lobes causes a positive displacement of volume that moves the sludge. So you can pump just about anything with this type of pump. Okay. The shafts go relatively slowly, okay? Now the challenge with this kind of pump is you have no room. There's very little space to try to put a seal in there, right? And forget a dual seal, right? It's almost impossible to get a dual seal in there. So, what do? So this is an example of a low flow DRM5, and you notice the massive amount of space they have in that stuffing box.
Absolutely.
There's your packing gland right there, and there's your flush line for your packing, right?
Okay.
So the problem in this kind of service is the sludge gets into the packing, abrades the shaft, then you got to replace the shaft and all the rebuild, and it's a pain.
Yep.
So how can you improve that with a mechanical seal? So these was actually some of the problems that the customer listed for us, which was kind of interesting. They had leakage and premature bearing failure when they washed down these pumps. Packing freezes inside the box. Freezes, that's the thing about that one. Flush water is very high. So what happens is when it starts out, your flush usage is relatively low, but as the packing wears the sleeve, that intimate contact between the sleeve and the shaft opens up, and then they start using a lot of water, and it gets expensive. So that's an issue. Obviously, it affects the efficiency of the process, and they pay by the gallon to dispose of the sludge. This particular plant did, and obviously safety and housekeeping. So those are some of the challenges. So they were looking for a better way to do it. So what they did was they worked with a manufacturer and mounted a mechanical seal here, and inboard of the seal they mounted a polymeric seal, right? So these shafts move slowly, so they're not high-speed shafts. So with slow-speed shafts, what you could do is use a polymeric lip seal type element inboard of the mechanical seal. And what that does is going to reduce water usage going into the equipment, but it's going to isolate the seal and lubricate the primary seal and protect the primary seal, right? So it's not a dual seal, but it's 3/4 of the way there.
Absolutely.
Right? So could you take water out? You could. They didn't. They reduced their flush rate substantially, right, to 5 to 7 gallons per hour.
Which of course is the end goal.
That's it, right? So yeah, we don't have a gallon a minute. Now we got 5 to 7 an hour. That's a much better situation.
Huge savings as
right?
well.
Right. So you're protecting the seal, and you're reducing your flush rate. Now, how do you know that the lip seal is worn? By the flush rate. So you monitor the flush rate. That starts to climb. You know that lip seal is worn. It's probably time to replace it.
Absolutely.
Okay. So there's a way to do that. And in sludge processing, and this lists all the sludge concentrations, 4 to 6%, not uncommon. Spirotrack active bushing technology is viable with hard face, and a lot of these services without a flush. If you get the interference fit design, if you have the split design, it will require a flush because there's no way for the air to get out.
Yep.
Generally better at higher speeds, surface speeds, so slower speeds, not as efficient, right? That's where you want to think about isolation technology or dual seal, something like that. So that's just kind of general guidelines. These are our standard recommendations. A non-split seal, hard face, flush, again, same idea, is our sort of standard recommendation. However, folks have done it differently. So here is a digester transfer pump, and this particular one happens to have a dual mechanical seal, and it has what's called Plan 54. So Plan 54 takes fluid into and out of the dual seal. It's piped from the plant, right? Now, let's see if I can put this one here. The thing is, when you have water going into and out of the dual mechanical seal, that gets expensive. A gallon a minute, 2 gallons a minute, right? It's a lot of water, right?
Absolutely.
Now, so the question is there a better way to do it? And it turns out there's a device, there are a series of devices that monitor the temperature of the process and the heat generated by the seal. And when that temperature increases to a level where cooling is required, it allows a valve to open on the drain side. So that valve will then only allow as much water as is needed to cool the seal. Remember, the most important thing with this device is that the pressure inside the seal will be higher than the sealed fluid. In sludge, that's the key thing, right? Getting water between that primary seal and keeping the sludge out. So the beauty of this device is you only use water you need when the pump gets hot.
Perfect.
Right? So all that water that's flowing through that seal stops. Now it's just the pressure, which is really all you want.
Absolutely.
But this is your insurance policy, right? So if it gets hot, you get flow, you're not going to fail the seal. So these devices will generally stay closed.
Okay.
They're closed most of the time. And the beauty of this device is if the pump's not running, you're not using water. If the pump's running and it's cold outside, you're not using water.
Yeah.
If the process is warm, generally you're not using water. If the process is hot or the seal gets hot, then you use some water. The use is very low. Generally, the worst case scenario is you will save 90% of the water that you would use with Plant 54. Worst case.
And that's the worst case.
That's the worst case. So these are very helpful. So this is kind of like a modified Plan 54, and it's really a water savings plan is what it is. So we talked about 53P earlier. This is another way to do it. So you could have a tank, and this tank you can set up with fluid, and you can pressurize this tank with some sort of a gas, compressed air, whatever, and then set a regulator with water supply. So the beauty of this is that if the seal uses fluid, which it will, it's going to use a little bit of fluid every month. And when I say a little bit, think about like a half a cup is normal, right? Okay. That fluid will automatically be replenished because if the fluid level drops, the pressure drops here, this regulator will open and then fluid will automatically be replenished into this tank. So you don't have to babysit this thing because that's one of the issues with dual seals is babysitting. However, if the inboard seal fails, you'll start to see this flow meter rotate, and that tells you that that inboard seal has failed. So the beauty of this plan, Plan 53P, is that the water is in a closed loop, right? And you don't have to babysit. So instead of the IntelliFlow approach, where you have to pipe water to the seal, this you could use in a relatively isolated place, right? So this arrangement does not require a large supply of water, ever, right? Unless the seals fail. You could set up a pressure switch or a flow switch. So if this was remotely located in your plant and that flow switch went off, it could trigger into a control room so you know that, hey, that seal's starting to use water, there's something wrong with it, right? So that's the beauty of this plan. So you don't really have to babysit that guy either. So here's an example of a digester recirc pump, and this particular pump has a slurry seal. So it turns out that there are mechanical seals that are better in slurries than others. They have certain design features that make them better in slurries than others. Things like springs that are designed to be completely outside the seal, micro-polished dynamic O-ring surfaces, seal faces that have the exact same diameter to avoid wiping and damage. So this is an example of one, and it turns out that when you talk about grit pumps and some of the sludge pumps, they have adequate room for slurries, seals. And slurry seals are designed to run with or without flush up to 40% solids in service. Technically, the ones that I've seen in settling slurries are designed to run up to 40% without a flush. So, so that is another option. What's the bad news? They're more expensive. So like anything else, they give you more, but you get more. So, all right, so that's that one. And we have our fourth poll question. When sealing wastewater service, the key strategies are isolation from the process with a flush, dual seal with a higher pressure barrier fluid, use spiral track device to use the energy of shaft rotation, use hard faces to resist abrasion. I didn't spell that right, sorry, I meant resist abrasion, or all of the above. So let's see what, oh, what happened?
It disappeared.
Oh, let me get that poll back up, folks, sorry about that. There we are. Sorry about that. Don't let me point and click, Nick. It's dangerous.
Oh, I'm sorry.
All right. So how many should we wait for? Answers should we wait for here?
We'll give a few. We'll give a few more. Seems like everybody's going to answer the same
good.
thing now.
Yes, I think we all agree.
All right.
All of the above was really what I was looking for. Yeah, exactly right. I mean, if you can have a flush, you want to isolate the seal from the process with a restriction bushing or a throat, some kind of a 14K or something like that. Make it as big as you can. That's one way to do it. If you cannot have a flush, you could use a dual seal. You might be able to use a spiral track, hard face, spiral track, but you definitely want to use hard faces to resist abrasion. So all of the above. Exactly. Okay, very good.
This time you can end the ball.
Okay, sorry about that. We had a little pole problem. All right, so here's another example. This is another example of a slurry seal in a digester recirc pump. And this is actually our old 156 slurry seal. Let's see the leaf springs here. This particular one uses leaf springs. Those will never clog, right? Because they're completely out of the fluid. Split seals are like that. Our split seals are like that as leaf springs now outside. So they're a nice solution. Now, what's interesting is this particular one was used with an active throat bushing. So just because it's a slurry seal doesn't mean you wouldn't use an active throat bushing with it. You always want to, my opinion is you want to use as much technology as you can to solve your problem, right? This particular customer also piped a flush in because, they want to make sure it worked, right?
Absolutely.
So, hey, worst case, you put a little flush in, knows they have it valved off here, right? So just because it's piped doesn't mean you have to use it, right? You may find you don't need to use it, right? So, but it's always worth asking for that. And these are examples. This is the key technology. So it springs out of the fluid. This surface is micro polished to a 4 finish. These faces are the same diameter, and so they avoid wiping. And so, these are key design elements of a slurry seal. So that's what you're looking for in that technology. And here's a gravity thickened sludge pump, and the sealing device is here. And this one is a dual seal. And they ran Plan 54 right through that dual seal right there. And primary sludge right here, and this particular one is a split seal. They did use a flush in this case. They filled the box with the restriction bushing to minimize contamination. So, and another use. Here's another split seal right here. So when the fluid leaves the plant, the effluent, right, the clean water, right, you'll see a lot of folks will use split seals. Now the water is relatively clean at this point. No flush should really be necessary, right? So these are examples of that. So these are mechanical seals. They're all mounted on these pumps. However, these pumps are vertical. So the concern the customer had is, what about air, right? And time flush, which is not a bad idea. So that's examples of that. Okay, well, thank you, Nick, for co-hosting our webinar today. Folks, feel free to enter questions or comments in the chat box. And we do have a survey. We would appreciate your feedback. And that survey is in the chat box right now. So you can click on that survey and take that survey. And we'd appreciate your feedback. Please feel free to enter any questions in the chat box, lower left-hand side. Other than that,
it looks like we have some pretty smart people here.
Well,
questions.
I recognize a lot of these names, Nick. A lot of smart folks out there. So.
All right.